Hello, welcome back, everybody. Today we are looking at improper integral, part two, actually, type number two. And this is kind of like a continuation from last time when we talked about the improper integral type number one. Now, the difference between the two, just as a recap, is that type one improper integral deals with what happens if you have a domain that deals with infinity. So, meaning like your x value horizontally is going to infinity or negative infinity and so forth. Type 2 improper integral deals with infinity in the range. So meaning what happens if the function is not continuous there because at some value of x is equal to a, you are going to either infinity, negative infinity, or undefined or something like that. So first we're going to go ahead and define a few things, so then that way we can figure out how to actually approach these type of problems. So here in the first one, we are going to consider the following then, okay? If f is a continuous function for x that is between a to b, inclusive of a but exclusive of b, and is discontinuous at x equals to b, then we can write the integral as the following then. So you'll notice that in the picture, the illustration on the right hand side, we have a curve of f of x where it is defined everywhere from a to b except at b then. And so at b is where we have some sort of discontinuity, again meaning either it goes to infinity, negative infinity, or undefined or something. So the way it works is that we're going to take the integral that we're going to try to solve for and break it into or change it into a limit problem. So notice here we have a limit as t is our variable, is approaching towards b from the left-hand side. So that's why it's b with a negative on the top. And then we're going to go ahead and change the boundary so that it is going to go from a to t of f of x dx. So note that over here, even though that there are no infinity or negative infinity in the integral itself, it's because the graph is undefined at a certain point. That's why it's considered improper then. So we're going to have to change it then. And similarly, underneath it, you can see kind of like the illustration that is going to happen on the right-hand side. So in this case, if f is continuous for x that is between b to c, continuous all the way to c inclusive of c, but exclusive of b, and it's because it's discontinuous at x equals to b, then we can write that integral from b to c of f of x dx as the limit as t approaches towards b from the right-hand side of f of x dx. So we can go ahead and take that picture right there, and we can change the boundary of the integral so that it becomes a limit problem, so we can hopefully then solve for it. A few things to kind of cover just as like, just to tie up some loose ends. Just like last time, we can define convergence and divergence according to what we get as a result. So if you solve for the integral, the improper integral, and it does exist to be some sort of like real number, then we say that this is going to be convergent. But if you solve for the improper integral and you get does not exist, meaning that you get some sort of DNE or some sort of infinity, negative infinity, then we say that this is going to be a divergent improper integral. Okay. And finally, for the last part, if you have the following scenario where f is not continuous at some value b, where b is in between the interval of a to c, but then you can find the integral of each one individually from a to b, and then also from b to c, and they are going to be convergent. Then the result is that we can take the integral and break it into two parts then. Okay, so the rules are pretty much very similar to improper integral part one. So here we're just going to look at it, what happens if you have an improper integral due to your range restriction. Okay, so let's go ahead and try to do some of these problems to see how this actually works out. So here, I want to find or determine if the given improper integrals are going to be convergent or divergent. So here in my first problem, you'll notice it doesn't look too bad. But the thing is that if you notice the denominator, here x cannot equal to 5 because of a domain restriction. And my boundary includes that 5. So that means that this is an improper integral. So we're going to have to change it. By the way, on the right-hand side, you can see a picture of the curve, so you can see exactly what is it that I'm asking you to solve for. So the way we're going to write it, as we said, is that limit as, let's go ahead and say A or T, doesn't matter. Let's go ahead and use A, is approaching towards 5. And according to this picture, you're approaching it from the left-hand side of the integral from 1 to A of 1 over x minus 5 dx. Okay, so now we're going to go ahead and solve for the improper integral by taking the antiderivative. So limit as a approaches towards 5 from the left, as ln of absolute value of x minus 5, and then boundary from 1 to a. Plug in the upper bound, plug in the lower bound just to see how that works out. So limit as a approaches towards 5 from the left-hand side of ln of a minus 5, that's the upper bound, minus, for the other one, that's the lower bound, ln of absolute value of 1 minus 5. So let's see, for this part over here, this is going to be equal to ln of 4. So that is a nice numerical value, which I like. But for this portion over here, as soon as I plug in 5 coming from the left-hand side, with the absolute value of ln of x, graphically, what you're going to do is you're going to go to negative infinity then, because if you recall, the graph of ln looks something like this, okay? And with the absolute value, that means there's something on the left-hand side, but still, it's still going to go to negative infinity. So because you have negative infinity minus ln of 4, so that means that this is going to be divergent then. Okay, so meaning the numerical area under the curve from 1 to 5 right here is going to be, does not exist, or divergent, meaning that it's going to be like infinity or something. Okay, so that we can go ahead and write that down. Okay, now, does that necessarily mean that whenever you have a vertical asymptote like this, you're going to get a region that's divergent? The answer is not necessarily. So you're going to have to kind of like, try it out to see how that works out. Okay, so in the next one over here, we have the integral from 0 to 10 of ln of x dx. Now, note that over here, you can see that you have the graph once again on the right-hand side, and what is it that I'm actually asking for? So in this case, is this going to be convergent or divergent? Because, well, I want to know what's happening with this little area underneath, okay? So once again, it is going to be undefined at x equals to 0 because you cannot take the ln of 0. So we'll change this into an improper integral. Limit as a approaches towards 0 from the right-hand side in this case, okay, of the integral from 0 to a of ln of x dx. So we're going to have to take the antiderivative. Well, fortunately, just to kind of have it on the side, hopefully you guys remember this. The antiderivative of ln x dx is going to be x ln of x minus x. And this is using integration by parts. So hopefully you guys remember how to do it. Just to save a little bit of time, I'm just going to go ahead and put that in there just to so we can look at the important part of it. So limit as a approaches towards a 0 from the right-hand side. And then now we're going to go ahead and put in the antiderivative, x ln of x, and then we have minus x, technically ln of absolute value of x in this case, and then boundary from 0 to a. Okay, now when we go ahead and plug in the upper bound minus the lower bound, hopefully we'll get something nice out of it. Limit as a approaches towards 0 from the right, we first have a times the ln of a, and then we have minus a, okay? Then for the other part, that's going to be plugging in 0. So that's going to be my upper bound minus the lower bound. You're going to get 0. Oh, actually, hold on. I've been messing up the entire time because the lower bound is supposed to be a, not the upper bound. So let me go ahead and make that small modification if it's okay. So change these guys, change these guys, change these guys. Change this over here. Sorry about that mistake. Let's see. So this is a is on the bottom. 10 is on the top. So we're going to keep 10 and then a on the bottom. So let's see. Then the first one is going to be 10 multiplied by the ln of 10 minus 10. Okay. Whereas the lower bound is what we were saying earlier, which is a times the ln of a. And then we have minus a over here. Okay. All right, so that definitely does look kind of nasty. So we're going to have to kind of clean that up a little bit if possible. In this case right here, let's see. The first one, let me kind of like split this into 3 parts. The first part, that's fine. That's just a numerical value. So we'll just go ahead and leave that alone. So 10 times ln of 10 minus 10. The second part, well, that's where I'm going to go ahead and apply the limit. Limit as a approaches towards 0 from the right-hand side. And then we have a ln of a. Now, that's the problematic part. And then finally, for the third part over here, and let me use a different colored pen just to make it a little bit easier, is going to be minus, when you plug in a is equal to 0 in this case, you're going to get 0. So all this, a whole bunch of stuff do cancel out, so that's kind of nice. But it's really this guy now that I have to focus in. So this is now a matter of, well, how well do you remember how to solve with a limit? And as much as I like to, just go ahead and say that this is going to go to negative infinity because of this ln over here, that a could be a factor. And, pun intended, I suppose, in this case. So that means that we need to see how this actually works out. Well, let's go ahead and write it according to how we saw for limits back then if we didn't know how to deal with it. So limit as a approaches towards 0 from the right-hand side. This is going to be ln of a divided by 1 over a. Now, that's a tricky thing that you probably forgot. And if you're wondering, okay, well, why am I writing it this way? The reason is we're thinking L'Hopital's rule is going to help us save all of this, save us at the end of the day. Let me just go ahead and rewrite all the other stuff, which is over here. So 10 times ln of 10 minus 10. But more importantly, again, I want to deal with what's happening over here. So looking at the top part, limit as a approaches towards 0 from the right of ln of a, that is going to go to negative infinity. Whereas limit as a approaches towards 0 from the right of 1 over a, that is also going to go towards infinity in this case. So because we have 2 infinity right here, then that means that this is going to be an indeterminate form, right? Just like last time. And so therefore, we can go ahead and use L'Hopital's rule then. Okay, so L'Hopital's rule. All right, so let's see how that works out. If I were to take L'Hopital's rule, then that means it's going to be limit as a approaches towards 0 from the right. The derivative ln of a with respect to a is 1 over a, divided by the derivative of 1 over a's derivative is negative 1 over a squared. Okay, so that's each one derivative respectively. And let's see here. If I were to clean this up, this would give me limit as a approaches towards 0 from the right. Let's see, multiply both top and bottom by a squared. That will give me a on the top, 1 on the bottom, and a negative. So then that means that this is actually going to go towards 0. So with all that's left, remember, this thing carries over the entire time. So in the very end, the area under the curve is going to be 10 times ln of 10 minus 10. So that means that because this is a numerical real number, then that means that the area under the curve is actually, the whole thing is going to be convergent. So that's going to be this guy over here. Okay, so it's going to be convergent. Okay, so there you go. It goes to show you that just because you have a vertical asymptote doesn't necessarily means that you will have something that's divergent, because if your area under the curve is convergent, then that means we're going to be okay then. So now let's look at the last example over here. What happens if you have something that's undefined in between the interval, but instead of like at the endpoints? So here is an example of that. The area between negative 1 to 1 of 1 over x then. So what I need to do is, again, I need to break it into 2 parts. So limit, because x is going to be undefined at 0. So limit as a approaches towards 0. So let's first look at the left, okay? So from the left, I would write the integral from negative 1 to a, and I'm going to approach towards 0 from the left-hand side of 1 over x dx. Then I am going to have to do the other part too. So limit as, let's use a different variable just so that we don't get it mixed up, because sometimes that does actually happen. So I'm going to go ahead and say b approaches towards 0 from the right, and the integral from b to 1 of 1 over x dx. Okay, so solving for each part individually, hopefully that we will get something that's convergent and convergent, so therefore it's going to be defined then. So now that is going to give us limit as a approaches towards 0 from the left. That is going to be ln absolute value of x, and then we have the boundary from negative 1 to a. Okay, and technically that reminds me over here we should have had absolute value of x also, but hopefully that actually didn't that wasn't a factor. That was something minor that I kind of forgot, so it didn't change anything. For the other part, we'll go ahead and write that as well. So limit as b approaches towards 0 from the right hand side, and then we have ln of absolute value of x, and then boundary from b to 1. So let me go ahead and write this all in purple, so then that way we can distinguish the difference between the two. Okay, so limit as b approaches towards 0 from the right. Okay, so remember, this guy right here, that is for this piece right here. Whereas this guy right here, that is going to be for this piece right here. Okay, so now we're going to go ahead and finish this off. For this one, that is going to say limit as a approaches towards 0 from the left. That is going to be ln of a and then absolute value. And then we have minus ln of 1 in this case because it's the absolute value of -1. So that's the first piece. And then we have plus for the other guy, limit as b approaches towards 0 from the right. And then this is going to say ln of absolute value of b. And then we have minus ln of, oh, sorry, the upper bound is actually 1. So this is going to be ln of 1 right here. And then this guy is going to be limit as b approaches towards 0. Oh, actually, wait, I did write the limit already. Sorry about that. Making mistakes left and right. Oh, no, that's not good. Limit ln of absolute value of b. Okay, so there it is. Okay, so here is where it's critical, because if I had used the same variables, a for each one of these, some people might have said that, hey, these two guys right here would have canceled each other out. But that doesn't work, because look at it carefully. One is approaching towards 0 from the right, whereas the other one is approaching towards 0 from the left. And I can't actually combine them together because, well, they're two different limit problems. Okay, so we can't actually use the same variables if possible. So try to, stay clear of that. But nonetheless, this guy right here, then the result is that you are going to have negative infinity for the first part, because as a approaches towards 0 from the left, absolute value goes to negative infinity. And then we have minus 0. And then this guy over here, that is going to go towards negative infinity as well. And let me see here. I feel like I made a mistake. 0. Oh, no. I'm sorry. I messed up right here. This part. Oh, sorry. That actually goes to 0 because of ln of 1. My fault. Okay, so let me go ahead and change that. Okay, so that is going to go towards 0. And then this last part right here is going to be minus ln of b, and then so if I apply the limit there, it'll be negative infinity. So that is going to give me infinity. Now, once again, this part right here, just because you have infinity minus infinity, that does not mean that it's equal to 0, because sometimes those area in between the two are not exactly the same thing. Even though in this case it is symmetric, we just still don't consider it the same, because maybe it's not the same in some other equation. So in the very end, we say that this is actually going to be divergent, because you could not solve with a limit over here, and you cannot solve with a limit over here. And these two right here, they do not add up to be the same thing. Okay, so be very careful. So in conclusion, this guy right here is divergent, and then this guy right here is divergent. Even though they are symmetric and technically are the same area, but because they are dealing with infinity, we just say, hey, you know what? I'm not going to touch it. We're just going to go ahead and say it's divergent overall then. Okay. Now, I do have some final notes that you guys want to consider, and these are two kind of like, things that you have to make sure that you don't make a mistake of. So let's say I gave you an integral problem, like say from -2 to 5 of 1 over x dx. Find the area under the curve from -2 to 2 to 5 of 1 over x. If you were to just solve for the antiderivative, right, and then using FTC2 and do exactly the following, okay, this right here would actually be the wrong answer, because if you recall correctly over here, if you look at the very beginning, x is defined not at equal to 0. So that means that you actually have to use an improper integral of what we did. And then if you get a numerical value, if it's going to be something that's real, then that means it's convergent. But if you get something like, say, it's infinity, then that means it's going to be divergent. Okay, so this right here would be the wrong answer then. Okay. Then for the other one is that, well, is there ever a case where you have infinity in both the domain and infinity in both the range as well? Because note in this scenario here, we have x is not equal to 0, x cannot equal to 0, and x cannot equal to -1. And that is somewhere between -10 to infinity. In addition, we also have an infinity over here. So does that mean that we have to do a double improper integral? The answer is no. You don't have to worry about the scenario over here. If you ever do, then somebody's just trying to pull your leg. It's definitely hard enough to do just one single improper integral versus double. All right, so thank you so much for watching. I will see you guys next time and have a good one. Goodbye.